Long jump is an athletics field event that consists of an intricate speedy run that has an explosive takeoff from a 20 centimeter wide wooden board. From biomechanics and Newton's laws, the forces from the run-up and the ground send the athlete flying into the air, landing in a pit of sand. The long jump consists of 4 phases: the approach, the takeoff, the flight, and the landing. In the long jump event, the athlete's objective is to obtain maximum displacement of the center of gravity in the horizontal direction. In a horizontal jump, the athlete endeavors to get their feet as far forward as possible without falling backwards when landing. All 4 of these phases contribute to the accuracy and success of a long jump. A key element in any sport is that every individual has their own technique. Demonstrating a technique is a good tool used for beginners. However, as a coach or teacher, the aim is to illustrate what to do and not how to do it. The approach. The approach is the most important phase for setting up the success of the overall jump. The purpose of the approach phase is to develop an optimal horizontal velocity and adjust the body into a position that will be beneficial in the takeoff phase and allow the takeoff foot to be accurately placed on the ball without fouling. During the approach phase, Newton's first and third laws of inertia and action-reaction are represented as the athlete approaches the wooden board. The athlete starts to sprint towards the board to take the jump. As the athlete's feet meet the ground, it produces a downward and backward motion, therefore exerting a force in that direction. The reaction that the force produces is reflective of the athlete moving in a forward and upward motion towards the direction of travel. In simple terms, the athlete starts to exert a force against the ground, which leads to the momentum of running. The athlete also exhibits Newton's first law of reaction. Here, the athlete's forward and upward motion will continue its acceleration as long as there is a force exerted upon it. The forward and upward motion produced when the athlete continues in a linear motion towards the sandpit creates speed. During the approach phase, it is important to have the maximal speed to achieve optimal distance. As the run-up involves quick and powerful muscle actions at a maximal speed, it requires the fast twitch muscle fibers and simultaneous forces to effectively carry out the task. To produce a maximal reaction, the simultaneous forces of the muscles generate a great force against the ground to effectively carry out the takeoff phase. These simultaneous forces involve large muscle groups. In the case of the approach phase, this predominantly involves the quadriceps, hamstrings, calves, the core, and the arm motor movements. According to Hay, if the athlete is traveling at 100% maximal controlled speed, it will take the athlete approximately 45 to 55 meters, or the equivalent distance achieved in 6 seconds for the run-up. However, the larger the run-up, the more chance there is for error to occur. The center of mass is an important component in the success of the long jump, as it determines the horizontal and vertical velocity that is used for the accuracy of the distance. The horizontal and vertical velocity works as a relationship throughout the long jump because if one of these elements is not correct, the entire jump is compromised. In the last few strides of the run-up, the center of gravity significantly changes to a lowered state to improve the success of the takeoff phase. The athlete must ensure that the vertical and horizontal velocities are at their optimal standard, which relates to the center of gravity because if the center of gravity is not balanced before the jump, then the horizontal and vertical velocities will be severely affected and an unsuccessful jump is produced.
The takeoff phase. The purpose of the takeoff is to obtain vertical velocity while retaining as much horizontal velocity as possible. The takeoff distance is a function of the accuracy with which the athlete places the foot on the takeoff board and the body position at the instant of takeoff. Although performance in the long jump event is largely determined by the athlete's ability to achieve a fast horizontal velocity at the end of the run-up, the athlete must also use an appropriate takeoff technique to make best use of this run-up velocity. At the start of the takeoff, long jumpers place their takeoff foot ahead of their center of mass at touchdown to achieve the necessary and desired low position. Their body then pivots up and over the takeoff foot. During this time, the athlete's takeoff leg rapidly flexes and extends. In long jump, the athlete wishes to achieve maximal flight distance of the human projectile by launching it at the optimum takeoff velocity and takeoff angle. A large horizontal velocity at takeoff to travel forward and a great vertical velocity are desired by the athlete when launching the body into the air. Just before touchdown, the athlete pre-tenses the muscles of the takeoff leg. The athlete's takeoff foot strikes the takeoff board, exerting large amounts of force upon it. The flexions of the hip, knee, and ankle joints during takeoff are a result of the large loads imposed on them at this time. Fast eccentric actions occur early in the takeoff phase, enabling the muscles to exert large forces and therefore produce large gains in vertical velocity. Maximally activating the muscles of the takeoff leg keeps the leg as straight as possible during the takeoff. This enables the athlete's center of mass to pivot up over the foot and again generate vertical velocity. The instant of maximum knee flexion is a poor indicator of when the extensor muscles of the takeoff leg change from eccentric activity to concentric activity. Over 60% of the athlete's final vertical velocity is achieved by the instant of maximum knee flexion, indicating that the pivot mechanism is the single most important mechanism acting to create vertical velocity during the takeoff. During the last half of the takeoff, explosive extension of the hip, knee, and ankle joints is accompanied by a forceful swinging of the free leg and arms, placing the center of mass higher and ahead of the takeoff line at the instant of takeoff. This is believed to increase the athlete's velocity at takeoff. A low position into the takeoff is necessary to give a large vertical range of motion in order to produce upwards velocity. The takeoff velocity that a long jumper is able to generate is substantially greater at lower takeoff angles than at high takeoff angles. Therefore, the optimum takeoff angle is shifted to below 45 degrees. Newton's third law, action-reaction, notes that objects exert equal but opposite forces on each other. When a long jumper pushes down on the ground during their takeoff, the earth pushes back on them in the opposite direction, with the same size force at exactly the same time, and as a result the athlete moves in the opposite direction. This force is called the ground reaction force. The ground reaction force tends to change the speed and direction of the athlete's center of mass. An athlete's vertical takeoff velocity is produced by the vertical ground reaction force exerted on the athlete and initially acts to reverse the athlete's downward velocity at takeoff, therefore accelerating them upwards. A slight reduction in the upwards velocity is always experienced in the last phase of the run-up before takeoff. This is because the vertical force must drop down to zero at the instant of takeoff. The ground reaction force also has the tendency to produce angular acceleration of the athlete's body about its somersaulting axis. In long jump, the ground reaction force generates a forward torque about the athlete's center of mass. During the early phases of the takeoff, the torque produces a backwards acceleration, but quickly alters to produce forwards acceleration. Therefore, the athlete experiences a great forwards rotational impulse, leaving the takeoff board with an immense amount of forward somersaulting angular momentum.
The flight phase. The flight phase is an important area of long jump as it is designed to control the body's forward rotation at takeoff to allow for an effective landing. There are 3 different techniques used in long jump: the sail technique, hang position, and the hitch kick movement. But for the purposes of this video, we will be focusing on the sail technique as it is the natural technique our athlete possesses for our individual's abilities. The sail technique utilizes the forward rotation of the body during flight to bring the knees up into a high held tuck position before an extension of the body to allow for landing. Whilst in flight, the trunk needs to remain in an upright position whilst one leg is horizontal and the other, takeoff leg, is bent to create the forward trunk rotation and allow the back leg to be brought into the tuck without too much backward rotation restricting the landing. Another alteration can be made to the velocity at which an athlete performs a takeoff. This can alter the momentum going into the flight phase, and according to Newton's second law of motion, these external forces will impact on the flight phase of the jump. A change in momentum during the run-up affects the takeoff. That in turn affects the jump and the momentum involved in the flight, resulting in a shorter jump. The momentum change can also occur during flight alone. If the athlete's position is slightly altered, the jumper will lose momentum and velocity, causing flight disadvantages. The rate of change in momentum will all depend on the force causing the change and the way in which the direction of force acts. The units of linear kinetics also apply to long jumpers, as mass and force directly affect the flight phase coming out of the takeoff. The force distributed at takeoff produces acceleration to continue forward angular rotation in the flight phase, which helps achieve distance. During the flight phase, an athlete wants to orient the body segments to properly produce an acceptable landing. The objective with centre of gravity with an athlete is to obtain maximum displacement to remain in as much of a horizontal position as possible. The centre of gravity whilst in the flight phase remains high. However, when preparing for the landing phase, the centre of gravity needs to change from a high state to a low state. The feet positioning also changes, like the centre of gravity, from a tuck position to a linear extension without disturbing or causing undesirable effects to the forward angular rotation. The landing phase. The landing stems directly from the flight phase, so any changes in positioning close to the landing could alter the entire performance of an athlete. If an athlete leans forward during the final stages, it delays their touchdown and they are carried further along the parabolic flight path. This moves the centre of gravity closer to the feet, which reduces landing distance. However, if an athlete keeps an upright trunk, they decrease the reverse flight time but increase distance jumped. The changes in an athlete's magnitude and the direction of their reaction forces altering the incline of the legs to a horizontal position means they will generally land in a sitting position, which means they lose distance. The aim of a long jumper is to strike a compromise between distances and takeoff to preserve ability to rotate forward over the feet. The aim to landing is to cushion the knees by contracting hamstrings upon impact to rotate forward, thrusting head and shoulders over the knees to facilitate forward rotation. In doing this, the ground reaction forces pass behind the centre of gravity, yet again increasing forward angular rotation, causing athletes to spring forward in an effort to regain control. Newton's third law of motion stated that to every action there is an equal and opposite reaction. This is especially evident in a long jump landing. Athletes' action is to move legs forward. To land, the reaction to the rest of the body is equal and opposite, meaning if arms move forward and upward, legs will move forward and downward, which is necessary when landing. The thrust of arms upward and forward evokes a contrary angular reaction, assisting in the upward-forward rotation over athletes' feet, allowing heel imprint as the point of measurement.
Hi, my name is Dom. My goal is to qualify for states in the long jump event. In order to do this, I'll have to increase my distance in the overall jump.
Two-step, 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 two-step.
The first problem that the athlete is displaying is the psychological trepidation in the run-up, and as a result is affecting all other aspects of the long jump. When the athlete approaches the takeoff board, he starts to produce a stuttering movement and looks down at the board to reduce the chance of fouling. Producing this stuttering movement decreases the optimal speed and ultimately Newton's law of reaction. Since the athlete is reducing his speed, the forces exerted upon the ground are reduced, therefore limiting the reaction of producing a forward and upward motion from the ground. As the forces are limited in the approach phase, the speed will correlate to distance. If the speed is compromised, then the distance will be negatively affected.
The preparation for the long jump takeoff begins in the later phases of the approach run-up. The last few strides in the approach phase are generally longer than normal as a result of the athlete sinking their hips to prepare for takeoff, then raising them into the takeoff phase. Here we can see that the athlete is shortening his stride, shown through a stuttering motion, as he approaches the takeoff board, rather than lengthening it. By doing this, he has immediately reduced his takeoff velocity as this phase is heavily impacted by the velocity of the runner. Therefore, it can be concluded that the takeoff velocity steadily increases by increasing the run-up velocity. The most important determinant of success in long jumping is the ability to produce a fast run-up velocity, hence a fast takeoff velocity. As he approaches the takeoff board, the athlete lowers his hips, lowering his centre of gravity and placing it behind his front foot. As his foot is placed ahead of his centre of mass at touchdown, he now has the ability to produce his desired low position and low angle at takeoff. When the athlete plants his takeoff foot, his opposite arm should be thrown back and chin lifted as he pushes off the board. The athlete does not display these movements. Rather, he places his head down as if he is looking at the board and his opposite arm appears closer to his body than it could be. Due to his arm positioning, we can assume that his shoulders are not behind his hips, influencing his centre of mass and the angle of his takeoff, and therefore manipulating the overall vertical velocity of the jump. At takeoff, the takeoff leg is designed to be as straight as possible in order to benefit from a faster run-up velocity. This is because a straighter takeoff leg has a smaller momentum about the knee for the ground reaction force, and therefore becomes resistant to flexion. In this captured image, we can see that the jumper has a reasonably straight leg during his point of takeoff, resulting in less energy being degenerated by the leg muscles. In saying this, bending of the leg during takeoff is caused by the force of landing, making flexion of the takeoff leg unavoidable.
The athlete has demonstrated that during flight he naturally uses the sail technique. However, in his first few jumps he showed inconsistencies with technique and ability. In some jumps, as you can see, he failed to tuck his knees, resulting in a shorter jump and in some cases falling backwards upon landing. These issues cause a lack of forward angular rotation, causing the jumper to lose momentum and velocity, resulting in a shorter distance gained. By not tucking his knees, the athlete alters his external and internal forces, causing his centre of gravity to be disturbed and not create its desired effect. The centre of gravity needs to be transferred from high to low to allow for ground reaction forces to be behind his centre of gravity and cause him to rotate forward. However, due to the untucked position, he isn't able to transfer his centre of gravity correctly, resulting in too much backwards rotation, causing him to sit upon landing.
I have three main aspects to focus on. 1, my run-up. 2, keeping my head up during takeoff. And 3, tucking my knees during flight.
Many young long jump athletes have difficulty keeping a maximal speed without having to worry about failing during the jump. When the athlete concentrates on not failing, their confidence is decreased and they focus their attention on the target context without producing the target behaviour. To increase the speed, adjust the run-up and reduce the trepidation of failing, the athlete will continue to perform the required movements in long jump. A mat will be put in place substituting the takeoff board in order to widen the takeoff area. As this behaviour begins to diminish, a new behaviour will emerge as another constraint is introduced. The athlete is then required to yell out the number on the piece of card that is held up at the end of the pit. The athlete is focusing on calling out the correct number as he jumps and is also taking off from the larger surface area. Therefore, the target behaviour is to keep his head up and look at where he is going, and to forget about the size of the board and fouling. Focusing on the target behaviour removes the target context of the wooden board and fouling, which overall enhances the athlete's target skill to keep their head up and not worry about fouling on the board. Since the athlete has shown emergent behaviour of yelling out the number as he takes off, the perceptual aspect of the original wooden board must be reintroduced to create the perception-action coupling.
How did increasing the width of the takeoff board improve and impact your approach?
The starting of my run-up was eliminated, allowing for fluency into the takeoff, and my fear of fouling was reduced.
Once this behaviour began to decay, the size of the number cards was decreased. This encouraged the athlete to maintain focus and keep his head up during the takeoff phase. What effect did Dylan have when holding up cards at the end of the pit?
Having to look and call out numbers during my jump had a positive effect on my performance. The application of this constraint forced me to keep my head up during the takeoff and not look at the board.
Many aspiring long jumpers don't follow through the correct motions whilst in flight. If long jumpers don't tuck their knees, they restrict optimum forward angular momentum, causing their velocity to retract and jumpers to not reach their desired distance. To create a positive transfer whilst focusing on the target behaviour of pulling the knees up, a box was placed in the front area of the pit. The box is placed in to gain the target behaviour of a tuck. This directly replicates what athletes are to do in long jump. The emergent behaviour at first may be to stop or even jump before the box, but given time the athlete will attune themselves to the positioning of the box and gain the tucking ability, which will then remain intact once the box is removed. The tuck allows for forward angular momentum gain during the run-up to remain whilst in flight and follow through into the landing.
Did you notice a difference in the distance of your jump?
I travelled further when the box was implemented in the jump.
Overall, by implementing a variety of constraints, the athlete was able to increase his jump and achieve his outcome goal. Introducing the mat to widen the takeoff board and positive self-talk decreased his fear of fouling. As a result, this improved his run-up as the horizontal and vertical velocity was increased. Decaying of this constraint was evident as the stuttering movements were gradually eliminated. The implementation of the number cards encouraged the athlete to keep his head up during the takeoff phase. As a result, his position into takeoff was improved as his centre of mass was behind his takeoff foot and his shoulders were slightly behind his hips. By tucking his knees up over the box, the athlete again increased his horizontal and vertical velocity. This allowed him to maintain momentum during his flight. The athlete found a compromise between distance and takeoff, allowing him to rotate forward over his feet.